What a pleasure it is to have you all here in person again. I mean, I love tech, as Yvonne mentioned earlier, but nothing beats this. So fantastic to have you here after a one-year break. I can't say how excited I am as well to hear all the great science that we're going to hear in the next few days. I have the enormous honor today of introducing another new award we've chosen to establish this year to honor early career scientists. With the support of Dr. Kurt Niebur, we have named our new award after Dr. Susan Niebur, who so embodied the spirit of young people starting in their careers and who so many of us in this community knew. Dr. Niebur received her PhD in physics in 2001 from Washington University and had an illustrious, although altogether too brief, career. Even before finishing her degree, she received the Best Student Paper in Astrophysics at the April 2000 meeting of the American Physical Society. She went on to become a presidential management intern at NASA and received a number of awards, culminating with NASA's Public Service Medal in 2011. When she was only 34, she was diagnosed with inflammatory breast cancer. This didn't stop her work. If anything, she put even more into her work, her family, and her community. She was a tireless supporter of women in planetary science, and I know many of you worked with her on this. I just spoke with Sarah Noble about this just before we started here, and incidentally, my 15-year-old daughter Claire is at the registration table, and so if any of you women planetary scientists care to talk with her about the benefits of a planetary science career, please feel free. She, of course, also supported many education and public outreach efforts in our community as well. She co-established a website, Mothers with Cancer, to help share her own lessons with others, and she was actively involved in social media through her blog on Toddler Planet and her Twitter feeds. On February 6, 2012, Susan passed away after her long fight. I'd like to share with you her mantra, still up on her website. All that survives after our death are our publications and people. So look carefully after the words you write. Excuse me. The thoughts and publications you create and how you love others, for these are the only things that will remain. Amazing words. There were many deserving candidates for this award, and the choice was very difficult. We've had the privilege at both Servie and NLSI to work with many outstanding students and postdoctoral fellows who contributed so much to our field. This inaugural year of the Niebur Award, we've decided to make two awards to equally deserving candidates. These individuals have both excelled in their fields and obtained international recognition for their accomplishments. Furthermore, they both embody the spirit of international cooperation that is so much a part of our of exploration science and of our institute. Each of them has been closely associated with our institute teams, and I'd like to give a special thanks to David Kring and Bill Botke, amongst our other PIs, for supporting these individuals so well in the past years. I'm very pleased to announce that this year's Susan Mann Niebur Awards have been awarded to Dr. Catherine Joy of the University of Manchester, United Kingdom, and Dr. Simone Markey of the Southwest Research Institute in Boulder, Colorado. If we could please give them both a hand. And Simone? Katie Joy is in England right now. She will be giving her talk from there. But Simone, if you could please come up, Yvonne, maybe.
So, Ricky, could you change the backdrop? I know we're going to go to Catherine in just a second, but let's get or maybe we could.
Or just turn it off.
So I believe we're going to go to Katie first.
Yes. Yeah, so I'd like to say a few words to introduce Katie Joy. Catherine Katie Joy obtained her PhD in Studies of Lunar Evolution from University College London in 2007, where she combined data from the European Space Agency's SMART 1 mission that you just heard about from Dr. Spudis, and studies of lunar meteorites. She then held a postdoctoral research position at Birkbeck College, where she studied data from the X-ray instrument on the Indian Chandrayaan-1 mission. In 2010, Katie took up a postdoctoral research post in Houston, Texas, where she was based at the Lunar and Planetary Institute and Johnson Space Center as an NLSI postdoctoral research fellow working for David Kring. She studied samples returned by the Apollo 16 mission in order to study the moon's impact record. In 2012, Katie returned to the UK to work at the University of Manchester, where she holds a Leverhulme Trust Early Career Fellowship to investigate the bombardment history of the moon and inner solar system. She has twice joined the U.S. Antarctic Search for Meteorites, ANSMET program, spending 2 field seasons on the ice collecting meteorites. Please again join me in welcoming and congratulating Katie Joy on this honor, and she will now give her talk. Thank you.
Thank you very much. Is that okay? Is the sound sounding all right? I don't have the privilege of having a chair dragged off the stage, so you're going to have to yell in my ear if I talk for too long. Okay, let's see if we can get this going. So I apologise that I'm not there in person. I'd much rather be in California right now than Manchester, although for once we have quite nice weather with no rain, so it's not doing too bad over here. So I hope joining you over the internet is going to work quite well and we won't have any technical difficulties. So today I'm going to talk to you about research that I conducted whilst I was based with David in Houston. And I'm going to talk to you about some lunar meteorites that we've been studying, and we have a paper in review at the moment which I hope will be published soon. So I'd like to acknowledge my co-authors on the talk that are listed on the first slide. So the motivation for our study is to study lunar samples in the laboratory and relate these to wider scale geological processes that we find on the moon and link these to remote sensing data to better understand global scale geological processes such as volcanology and impact processes. So the meteorites that I'm going to discuss today have been hypothesized to originate from the South Polar Basin. So the point of our study is to test that and relate these possibly to the basin structure. So a little bit of background about the meteorites. We have 185 meteorites that have now been collected on Earth. So this is lunar material which has been ejected off the moon and impacted and has travelled through space and through space and been placed across the planet. So these 185 meteorites have been found in places such as Antarctica, Africa, Australia and the Oman region. And this process to demonstrate this the huge number of new samples that we have that sample and access regions of the moon that were not sampled by the Apollo and lunar missions. So far we have about 68 kilograms of material compared with about 382 kilograms of moon rock that were returned by the astronauts and the sample return missions as well. So I'd like to draw your attention further, if you'd like to find out more information about lunar meteorites, to go to Randy Koratev's amazing website that he keeps up to date with all the new finds and scientific publication material and to investigate this in a little bit more detail. So the lunar meteorites that I'm going to discuss with you today are the DOFAR 925, 960, 961 and SAU 449 lunar meteorites, all of which were collected in the Oman region. They've been classified as impact melts brecciated lunar meteorites, and there's been lots of initial studies of these published in LPSC abstracts previously. So the significance of these particular meteorites is the fact that they've been proposed to originate from SPA on the basis of their unusual bulk rock chemical composition. They have unusual chemistries compared with samples that were studied by the Apollo missions. They're relatively mafic, but they represent typically non-Mare basalt lithologies. They also contain a significant incompatible trace element rich and iron-rich impact melt component, which has a similar chemical inventory to that that has been mapped from orbit by the Lunar Reconnaissance Orbiter spacecraft. You can see here a plot of thorium, which is a tracer for incompatible trace elements on the lunar surface, and the Dhofar lunar meteorites collectively have been related to the compositions that we see in SPA. So our study was to investigate this further, to study all of the different meteorites and then try and relate that to possible origin, and to try and tie down and test the SPA hypothesis in a bit more detail, to make that link between samples and the big picture. So a little bit about SPA and how we sought to test this. Well, we can use the chemistry of the Mare basalts that have been mapped in orbit from using the Clementine datasets, so the titanium datasets and the iron datasets collected by Clementine, and also the Lunar Prospector iron and titanium datasets as well. We have the ages of SPA has been proposed, although we haven't been there to sample it in person. This is one of the greatest questions within lunar geology, as SPA is believed to be one of the oldest impact structures. And so defining its age will help to bracket the age, the duration of basin formation on the Moon. From crater counting techniques, we have the basin age has been proposed to be anywhere between about 4.26 and about 4.3 billion years old. So we can kind of tie our sample ages in with that sort of information. And then we also have the broader scale surface chemistry and mineralogy information as well, which has been mapped from orbit. And studies recently that have come out this year include those by Hertzfried and Kring and Vaughan and Head, looking to see how the surface chemistry can be related to the differentiation of impact melts within SPA as well. So we have lots of lines of evidence that we can use to test these particular samples. So our methodology is we had some large specimens of these 3 different meteorites, which we then prepared thin sections of. And we studied using a variety of both chemical, mineralogical and chronological techniques in different laboratories. And all of this was made possible by the collaborations enabled by the NASA Lunar Science Institute node in Houston, with our collaborators both in and around the US and overseas as well, with Alex Nemchin in Stockholm and Tom Latham at the University of Houston. So this is just a quick link of the different types of analytical techniques and a careful analysis that we did on all the different samples. So to run through them in a little bit more detail, this is what the surface expression of the sample looks like when you just look at it optically. It's pretty small, it's only 4 millimeters by 4 millimeters in diameter, and you can see immediately that there's lots of different clasts and variable rock types encapsulated within quite a dark impact melt matrix. When you look at this in a bit more detail using the scanning electron microscope, we can collect maps such as this, which is a backscatter electron map, and this starts to reveal the mineralogical and textural diversity in a little bit more detail. We can do even neater things, whereby we collect chemical maps of the sample such as this, and then we can nicely colour recombine them, so we can start to map out the chemical variations within the sample to link that to the different types of lithologies in a little bit more detail. So you can see material which has been sampled that is very plagioclase rich, this is what it's expressed with the white colorations, and material which is more mafic, these are kind of the purple and the red tones. So in terms of texturally, the sample, this particular sample is an impact melt breccia. You can see here a close-up backscatter electron map. It has lots of different classes of lots of different mineral fragments contained within a mafic glassy matrix. So these things are incredibly complicated and require quite a lot of work to try and pick apart. The Dhofar 961 lunar meteorite stone is very similar to the other one. It's a little bit more lithologically diverse. It has areas within it that are texturally similar to Dhofar 95 in that they have this impact melt breccia kind of matrix structure associated with them. But then there are other areas that are more lithologically diverse and have a much more fragmental matrix material. So they're not necessarily constructed within an impact melt environment, but just represent mixing of different lithologies. Dhofar 961 is also chemically diverse. You can see what a nightmare samples like this are to study in trying to understand all the different lithological origins, but they're a huge amount of fun to try and pick apart and to test all these different ideas we have about their origin and the types of rocks that are being sampled. SAU 449 was a little bit of a larger sample. It has a funny hook-like cut on it here due to the sample preparation. but again it is texturally diverse. We have some interesting array of different rock types within it, and you can see they have proportions of metal that have been sampled by impactors that have hit the lunar surface and then have been incorporated into this breccia as well. And then they have a diverse matrix. Other authors that have studied these meteorites previously have reported impact melt spherules within them, suggesting that some of these samples might represent have a regolith or a surface chemistry, a surface component associated with them. But in our study, we didn't find that. So it is untested as of yet if these are regolith material or if they just contain small class and regolith material which should be mixed in the impact setting. And here is one of those chemical maps again. So what did we do? Well, we carried out a lot of work looking at the chemistry of the samples, and we classified all the different material within them and the proportions of the different rock types to try and pick these things apart. And then we age dated components we found using in situ uranium-lead age dating techniques. So there is a series of the mineral phosphate minerals, apatites and meryllites that are distributed throughout the matrix of these samples that have a range of ages from about 4.3 billion years ago to about 4 billion years ago, representing pre-Nectarian material and different types of pre-Nectarian geological events. To talk about some of these rock types in a more detail, because these are the ones which might be able to relate to SPA types processes, we found an array of interesting crystalline impact melt breccias, so material that was completely melted and then recrystallized in an impact melt setting. These have a poikilotic texture. Chemically, they're actually quite similar to some of the Apollo impact melts. They have similar types of mineralogy and contain small fragments of meteoritic metal within them. When we age dated the phosphates within this particular class type, they have a continuous age spread of ages between about 4 billion years and about 3.8, 3.9 billion years ago, putting an upper age limit on the types of impact melt processes and the subsequent thermal disturbance history of these types of impact melts. We have a wider range of class-bearing impact melt breccias, so these would be impact melts which incorporated local rock during the cooling event. They have appreciably different compositions to the types of impact melts that we sample with the Apollo material, so we note a similar thing to previous studies here. They have kind of intermediate melting iron and aluminium mixing compositions between different types of lunar samples, and they probably don't require melting of a high magnesium sweet or a high alkali sweet, rich material, suggesting they sample different types of rocks than those that were sampled by the Apollo missions. Interestingly, they do have lower concentrations of the incompatible trace elements than that we map from orbit from looking at sample molecular material. So this might preclude an origin in certain parts of SPA. We have an interesting array of granulite samples. So these are metamorphosed northacitic gabbro norites. We don't interpret these to represent purely igneous rock types because we find a lot of chamacitic meteoritic type metal within them, and so possibly these could represent some sort of metamorphosed impact melts or some sort of coarse grained differentiated impact melt sheet material. We conducted age analysis of one of these particular samples where we could find an apatite, and it had an age determination of about 4.08 billion years ago. We have a series of Mare basalts within the sample, suggesting we've had sampling of volcanism. When we look at the chemistry of these basalts in a greater amount of detail, we see two different trends. We sample some low titanium basalts, but dominantly we're sampling very low titanium basalts on the basis of mineral chemistry associations. So this suggests that the source region that sample these meteorites is dominated by very low titanium basalts rather than other types. So this precludes an origin in places like Mare Tranquillitis on the near side of the Moon and places within Oceanus Procellarum. Okay, so testing this SPA origin in a little bit more detail, we went to the high-resolution lunar prospector calibration of different elements to search for places on the Moon where these best match the composition of these different meteorites. And we did two things. One, we tested the bulk composition of just DOFAR 961. It has a slightly elevated composition compared to the other stones, and then we tested an average of the different stones as well to see where these things compare and contrast with Prospector. So for the DOFAR 961 stone, they have the most similar composition to places on the outside edge of the Procellarum creep terrain and are consistent with some places within SPA. However, this meteorite has been noted to be maybe unrepresentative. And so we prefer to use the results from the average DOFAR group searches, which reveal a large amount of regoliths around the moon that best match SPA, such as areas within SPA itself around the Apollo basin, but other crypto-Maria regions and eastern Mare along the eastern limb of the moon as well. Okay, so in terms of testing it, I've just seen a message saying I only have 1 minute left to kind of quickly try and wrap up. Are we comparing and contrasting our results to what we see that have been mapped from orbit? Most of the Mare basalts that have been mapped within SPA, these are volcanic products that were intruded into the basin, are low TI to high TI in composition. So the results of the Mare basalt samples within our meteorites are not consistent with these types of lava flows. However, there are crypto-Maria that might not be exposed at the surface of SPA, which might be VLT in composition, and so this doesn't necessarily rule out an SPA origin. In terms of an age date, this is the range of the basin ages that have been established so far from crater counting techniques. The younger impact basins that have been imprinted reveal that have younger ages between about 4.1 and about 3.9 billion years ago, with the lava flows being a lot younger. So the age dates that we've recorded in our samples that go from about 4.25 to about 3.89 billion years ago could be consistent with SPA, but we can't say for sure if any of these particularly sample an older SPA style event, and they could potentially have been overprinted by younger basin forming events at about 3.9 billion years, consistent with places like Apollo and Schrödinger, some of the younger basins. So the jury's still out. It's incredibly difficult to interpret where a lot of the lunar meteorites come from. They reveal new things about the moon, and certainly the DOFAR meteorites may have come from within the South Polakian Basin, but without better ground constraints on the age of SPA and also the in-situ surface chemistry, it's pretty difficult to tell. We're currently conducting argon-argon analysis, which maybe can improve some of our understanding of the ages sample within these intriguing meteorites. But ultimately, if we want to go back and date SPA and to constrain the duration of basin formation on the moon, a sample return mission which can actually grab material from the surface and return it to Earth from a known location with geological context is always going to be best. So although I'm a huge fan of lunar meteorites, returning samples from the lunar surface is going to be a really important science for the next foreseeable future. And just to finish off, to give some acknowledgements, I'd like to thank everybody who have helped me through my career so far, and particularly for the opportunities afforded me by David Kring and involvement with the NLSI Institute at LPI and JSE. And I'll leave it there, and I think hand over to the next person. So thank you very much. And I can't hear anything anymore, so if you're saying things, thank you very much.
Yeah, it's so great to have you as one of these award winners. So we're going to move on. We don't have time for questions. I want to let you know, for those who have been paying attention to the clock, that we are running a bit late. What we're going to do is go into lunch a little bit, and we'll make up the time that way.